So have you ever stopped to think about what connects, say, life-saving medicines with the refrigerant in your car? Well, it all kicks off with something incredibly simple. You can think of organic chemistry as building with the universe's most common Legos, taking these really basic blocks and creating something amazing.
And the two most fundamental bricks in that Lego set? Carbon and hydrogen. They're everywhere. When you stick them together, you get what we call hydrocarbons. They're the simple foundational skeletons of pretty much all organic life as we know it.
But here's where things get really cool. What if we take one of those simple hydrogen bricks and we swap it for something with a superpower? Something that gives the entire molecule a brand new chemical handle that it can use to interact with the world. Let's find out what happens.
That simple little swap, it creates a whole new family of molecules we call halo compounds. But to really get what they are, we first need to understand the two basic playing fields where this swap can even happen.
Okay, so on one side you have your aliphatic hydrocarbons. These are just open chains of carbon atoms. Picture a straight line, or maybe a path that branches out. Then, on the other side, you have aromatic hydrocarbons. These guys are stable, closed rings of carbon atoms. The most famous one, of course, is benzene. So you've got two totally different starting points for our swap.
So let's say we do our super-powered swap on one of those open-chain aliphatic structures. What do we get? A haloalkane. It's that simple. We've just taken a basic hydrocarbon chain, plucked off a hydrogen, and snapped on a halogen atom right in its place. And what if we do the exact same thing, but this time on one of those super stable aromatic rings like benzene? Now you've got a haloarene. See, it's the same fundamental move, swapping hydrogen for a halogen, but because the starting structure is different, you end up with a completely different class of compound.
So we've made the swap. But here's the thing about organic chemistry. It's not just what you add that matters, it's precisely where you add it. Trust me, location is everything.
And this is just a crucial point. I mean, the properties of our new molecule can change dramatically based on the exact location of that halogen atom. Shifting it by just one single carbon atom can make all the difference in the world.
And this right here shows that principle perfectly. Look at the allylic halide. The halogen is attached to a carbon that's next to a double bond. But in the vanillic halide, it's attached directly to a carbon that's part of the double bond. That tiny little shift in placement creates two fundamentally different compounds, each with its own unique properties.
So you might be asking, why is that tiny shift such a big deal? Well, it all comes down to the carbon's bonding style, or what chemists call its hybridization. That allylic carbon has what we call an sp3 style, while the vinylic one is sp2. This difference in how the carbon atom itself forms bonds is the real reason they have such different chemical behaviors.
Okay, so we know where it is matters. But what exactly gives the halogen its superpower in the first place? Well, the secret lies in a property that basically paints a giant target on part of the molecule, making it super reactive.
And that secret weapon is called electronegativity. You can think of it as an atom's raw power to pull shared electrons in a bond towards itself. It's like a game of tug-of-war for electrons, and believe me, the halogens are the heavyweight champions.
Let's just break that down real quick. You start with a carbon and a halogen sharing electrons in a bond, but that super electronegative halogen starts pulling those electrons closer and closer and closer to itself. This creates an imbalance, right? You get a slightly negative charge on the halogen and a slightly positive charge on the carbon. And that polarity, that little imbalance, is the chemical handle we've been talking about. It creates the perfect spot for other molecules to come in and react.
And get this, not all halogens pull with the same amount of force. As we go down the group, from fluorine all the way to iodine, the atoms get bigger. This means the bond between the carbon and the halogen gets longer, and the bond itself actually gets weaker. The carbon-fluorine bond, it's short and incredibly strong. But the carbon-iodine bond is long and much, much easier to break. And for a chemist, knowing that is key to making specific reactions happen.
So we've got these reactive handles. We know about their bond strengths. But why does any of this matter outside of a chemistry lab? Well, because this one simple atomic swap has had an absolutely massive impact on our world.
Just look at this list for a second. We're talking about essential solvents for huge industrial processes, life-saving anesthetics like chloroform, the refrigerants that cool our homes and our food, key ingredients in modern medicines and pesticides, even the stuff inside fire extinguishers. Every single one of these technologies relies on the unique properties that come from these halo compounds.
I mean, just think about that. One simple action, swapping a tiny hydrogen for a halogen. A minuscule change at the molecular level was enough to build entire industries from the ground up and completely revolutionize fields like medicine. It's a pretty powerful reminder of how small changes can lead to enormous consequences.
And that kind of leaves us with one final thought. We've seen how just one fundamental tweak to the basic building blocks of life has completely reshaped our reality. It really makes you wonder, what other simple swaps are still out there, just waiting to be discovered? And what new worlds will they unlock for us?